So thanks for inviting me to the conference. It's a very nice conference. I'm sorry I wasn't able to participate in person, but I enjoyed the talks a lot. And I also have never been to Arkansas, so I wish I could have been there for that reason as well. But unfortunately, we'll have to leave it for another time. So I'll talk about fluid dynamics and specifically Euler equations on general domains. So particularly interested in singular domains. And these results that I will present are joint works with Lakav separately, and then with my student Han as well. So these are containing 3 distinct papers. And so let me see whether, oh, this works. Okay, good. So I'm talking about the 2D Euler equations. Let me ask you, do you see this the top of the slide?
Yes.
Okay, good, because I have something in the way, but that's probably because I'm the one sharing. Okay, so 2D Euler equations, and so they are here. U is the velocity, and P is the pressure, and we're on some bounded domain, and here is written in RD, but I'm talking about 2D, and of course there is the usual no flux boundary condition, so the fluid doesn't flow through the boundary, it flows tangentially to the boundary. And in 2 dimensions, we can quickly get rid of the pressure, which is the most annoying term, by taking the vorticity or looking at the vorticity of the velocity u. And so then the 2 equations simplify to a single equation, which automatically will have the velocity incompressible, which is, of course, the second equation here. And the velocity can be determined from the vorticity by this Biot-Savart law, where we take the vorticity, which is now a scalar, scalar function on the domain, domain D, and we take the inverse Laplacian. This is the Dirichlet Laplacian. So we get a function that is 0 on the boundary of the domain. And then when we apply the perpendicular gradient, we get the vector field velocity, which will be tangential to the boundary of the domain because this function is 0 on the boundary. And that function is, by the way, called the stream function of U. And I'm talking here about domains that are going to be simply connected and bounded in R2. And so the main questions here are the solutions on these domains unique? And very closely related to that, can particle trajectories reach the boundary of the domain in finite time? Now, this can certainly happen if we have general vorticities, but a standard theory, this goes back to Udovich, is to consider vorticities that are in L infinity, or you can make them smoother if you'd like. And in that case, actually on smooth domains, this is not possible. And of course, that's understandable because the velocity, particle trajectories, they basically are just the solutions of the OD with the velocity on the right-hand side. So they are just the trajectories where the fluid particles are going. And because the velocity is tangential at the boundary, then obviously we should expect the particle trajectories to not reach the boundary in finite time. But of course, if the domain is a singular domain, then this can become an issue. So, so as I said, let me just go very quickly through the history for bounded vorticities. There are works, this goes back to Volodymyr-Helder and more in the generality of bounded vorticities to Udovich. And basically what happens is that the velocity is log Lipschitz. So this is, of course, a famous result. And that also gives us in the case of smooth vorticities, the double exponential bound on the growth of the gradient of the vorticity on smooth domains. So now existence can be obtained on more general domains and even more with more general vorticities, but there is an example by Fischig, which includes forcing, but basically suggests that when we go beyond bounded vorticities, we might not have uniqueness. So if we are interested in having well-posedness theory, then it will be necessary or it seems to be necessary to restrict ourselves to bounded vorticity. So that's what I'm going to be doing here. And so then, of course, we know everything on the smooth domain. So how about domains with some singularities? So if there are finitely many of those, and so these will be corners, and in between those corners, the domain is going to be smooth enough. So there is a result of Lakavmi-Wang, where it's C2 alpha, and Diplo-Tema, where it's C11 in between these corners. And also these corners have to be acute corners. And in fact, in these papers, they have to be exact sectors. So exact cones, if you'd like. So then indeed uniqueness does hold. And the reason for this is that the velocity again is log Lipschitz even at these corners. Okay, that's the crucial ingredient in the proofs. But of course, this is a very limited result. So, but the reason for that is that once we are outside of this family of domains, then the log Lipschitz of the velocity that just does not hold. For instance, if we have obtuse corners, then the velocity is only Hölder in the neighborhood of such corners. And if we have corners with angles greater than pi, then velocity is even unbounded at those corners. So obviously, you know, this ingredient is not there, and actually this is still an open problem what happens in that situation. And one way to sort of sidestep this issue is a lemma that we proved with Lacav. And basically it says that as long as the vorticity stays constant in a neighborhood of a bad part of the boundary, and the bad part is the part of the boundary of the domain where the boundary is not C2 alpha for some alpha positive. So as long as the vorticity stays constant near that, then actually weak solutions are unique, but not all weak solutions, but Lagrangian weak solutions. So what does it mean to have Lagrangian solutions? That's just the solutions that we really think about as what solutions should be like. So there is some hypothesis on the regularity of the velocity and vorticity, but you know, you don't have to worry about this important vorticity is bounded. But then we take those particle trajectories, which solve this ODE, start at little x, and then we ask, is the vorticity carried along by the particle trajectories? Because remember, this is a transport equation with velocity u for the vorticity. So we should really expect that. And so if this happens for almost all x, and of course, in particular, this includes the assumption or the requirement that the particle trajectory for almost all points x stays inside the domain up to time t, and of course that's for all time. So up to time infinity if we want to go all the way to time infinity. Okay, so then as long as this happens, so particle trajectories, almost all of them stay inside the domain and carry the vorticity, then the solution is Lagrangian. And so this proves that Lagrangian solutions are unique as long as they don't carry the vorticity, or at least they only have a constant part of the vorticity near the bad part of the boundary. Okay, and so let me just skip the proof. I don't think I have the time. How much time do I have for this talk? Is it 45?
Yeah.
Okay. So as I said, this is actually not proved yet basically at all. It's completely open. What to do when the vorticity or the non-constant part of the vorticity hits, let's say, these bad corners, the obtuse corners, corners greater than angles greater than pi, etc. The only result there is a result of Agrawal-Nahmod, where the vorticity is has a sign initially, therefore forever, and it sort of starts so that it is not constant near one single obtuse corner, but because of the sign, the non-constant part of the vorticity immediately gets carried away from that corner, and so then they also proved uniqueness. But it's sort of almost the same situation as if the vorticity just stays away forever from that corner. And so now you might think that, okay, so I might be able to do something if the vorticity is non-constant near the boundary, but it's only a good part of the boundary. And the problem there is that typically your vorticity is, or the non-constant part is going to be carried into that bad corner if there are such bad corners. And the reason is that, so for example, look at this domain here. At this bad corner, the velocity is actually even unbounded, but even if it's just an obtuse corner, so angle between pi over 2 and pi, then the velocity is Euler. And so if there is a chunk of the domain where the vorticity is not constant, let's say everywhere else or nearby this corner is constant, so the that chunk can be carried along and reach that corner in finite time because the velocity is Euler or even unbounded there. And remember, the velocity is tangential along the boundary. So one could do something maybe if there was an acute corner here, and the non-constant part of the vorticity would be touching the boundary here, then it can never go past those acute corners because the velocity is Lipschitz or log Lipschitz in those corners. But barring that, basically there's an issue with having the vorticity non-constant anywhere at the boundary if we have such bad corners. And so the other idea then is, how about just figuring out what happens when the vorticity starts non-constant everywhere along the boundary? And the question is, sorry, starts constant everywhere along the boundary. And the question is, would it remain that way? Okay, and that, of course, then immediately ties to the question I mentioned, which is, when do particle trajectories that start inside the domain reach the boundary in finite time? And so this is to do with the definition of these Lagrangian solutions. And in the case of those, we required that the trajectories stay inside D for almost all points X. But obviously, in this question that I just mentioned, we would really need those particle trajectories to never reach the boundary for all initial points from the domain. Okay, and so once we have that, we can have hope for uniqueness. At least we certainly would have uniqueness of all the Lagrangian solutions, but the question then also is, could we have weak solutions that are not Lagrangian? And by the way, if we do have a situation when a positive measure of particle trajectories reach the boundary, so this doesn't hold, then essentially we cannot hope for having Lagrangian solutions, because what happens is that some chunk of the domain gets carried outside of it in finite time. And because of incompressibility, that means there have to be some particle trajectories that enter the domain as well. And so there will be a chunk of the domain that is just the endpoint of trajectories that start on the boundary at some intermediate time. And obviously in that whole chunk, we cannot have the solution determined by the initial condition, if this happens. Okay, so, so how about now this question? We start to be with vorticity that is constant. You can think of 0 near the boundary. And then the question is, when do particle trajectories, or when can particle trajectories reach the boundary in finite time? And so Lacaze actually proved the first result when he had a piecewise C11 domain with actually no acute corners. This is sort of funny because the acute corners are the good ones and the obtuse and larger corners are bad ones. But his approach required no acute corners, and all larger corners were fine. And he also required assigned vorticity. And then he found a Lyapunov functional that allowed him to show that indeed, if the vorticity is signed and bounded on such domains, then no particle trajectory can reach the boundary in finite time. And as a result, he proved uniqueness of solutions. And I will show you that functional a little bit later. And then later, together with me, we we extended we proved the same result without the hypothesis of a sign on the vorticity, and we proved it with for domains with all corners, again finitely many corners, having angles strictly less than pi. So again, now obtuse corners are fine, but corners greater than pi are not good. And the question is why, and we found a different Lyapunov function. I'll show you that as well. And the question is why these angles greater than pi, how do they prevent or how do they allow the particle trajectories to reach the boundary in finite time? And so we also proved the theorem that shows that that is possible as long as you have at least one corner with angle greater than pi. So we can construct it simply connecting domains, which have a boundary that's smooth everywhere outside of that corner. And there are weak solutions with support initially being strictly inside the domain, such as particle trajectories that start inside the domain can reach this single corner in finite time. And the domain looks like this. And this is, of course, that offending corner. And the construction is sort of based on a similar idea that I had with Kiselev in a paper where we had this kind of double stadium domain. So the angle, interior angle here and here is actually 2 pi. So there are interior cusps here. And the idea was to construct solutions that developed or become non-continuous, discontinuous in finite time. And so these were solutions where there was vorticity 1 here and -1 here, and let's say 0 away from those two regions. Excuse me. And then very quickly, these two chunks joined here, and you got discontinuity across this axis in the middle. And so this is sort of a similar idea, but now you start with vorticity. The vorticity is, by the way, odd across this axis here and here. So now you start with vorticity that's non-zero inside the domain, and then you get carried in finite time towards this corner. Now, this doesn't mean that the solutions that will result will not be Lagrangian, because you are only carried to this corner if you start on the axis, because the solution is odd. So particle trajectory starting up here will stay up here, and down will stay down as well. So you can only get a measure 0 of particle trajectories reaching the boundary in finite time. So this does not immediately say that the solution is not going to be Lagrangian, but it does say that you can reach the boundary in finite time. And obviously that's going to be an issue as far as the idea or the approach that I described is concerned. So this is this all means that if you want to get into a situation that you might be able to show particle trajectories to never reach the boundary, then you have to exclude these bad corners. And so even if you may allow your boundary to be much more singular than just finitely many corners, you have to exclude points with interior angles to be greater, where interior angles are greater than pi. So at any point of the domain, you can measure the interior angle, and the interior angle has to be no more than pi. Except when the vorticity has a sign. This was the previous result of Lacave I described. So, so if you want the general vorticity, you have to do that. And then it turns out your domain has a property that's called regulated property. And so this comes from complex analysis, this definition. And basically what that means is that at every point of the domain, you have a forward tangent vector and a backward tangent vector. You don't necessarily have a tangent vector, but you have forward and backward tangent vector. So what that means is that, of course, here at all these points, you have a tangent vector. At this point, you just have a forward tangent vector, which you find by taking the usual limit, but you take this point here at the corner, and then you can take the points that are located along the boundary forward from that point. So if you go counterclockwise along the boundary, you just look at this point and all these points. And of course, then you get a forward tangent vector, which is pointing in this direction. And if you go to backward, or if you define a backward tangent vector that again uses these point and the points before, and then of course the limit is going to be this backward tangent vector. So of course the two differ, but they both exist, and they both are limits, one-sided limits of the same vectors at other points. So at these points you have the tangent vector, which is like that, and so the backward tangent vector is a one-sided limit of those tangent vectors, and the forward tangent vector is also one-sided limit of the tangent vectors at all these points. So so that's a regulated domain. We need those two forward and backward tangent vector, and they have to be have one-sided limits. And of course, this means these somewhat reasonable. So, for example, fractal domains are excluded out of this. Anyway, and so now the next results will be on such domains. Therefore, so Lipschitz regulated domains, and they also are by definition simply connected. That's in the regulated property. And we will also be looking at the tangent vector. And so there are two ways how one can parameterize the boundary that are natural. One is, of course, just by arc length. And we could do that, but it turns out in order to get a sharp result, which we are able to get, then we need to parameterize it using the Riemann mapping. So we take the Riemann mapping from the domain onto the unit disk in the complex plane. This is in 2 dimensions, of course. And then look at the point that's the pre-image of e to I theta. And we can, of course, do this for theta real. So that means we are just winding around the domains, the boundary of the domain multiple times, infinitely many times. And so look at that point and take the forward tangent vector at that point and call it beta theta. Okay, so in particular, if you go around the domain once, then your beta is going to be increasing by 2 pi, because of course, as you are going around the domain, you are turning to the left, and going once around the domain means you turn once to the left. Okay, so that's the setup. And I should probably actually, since I'm talking about this picture, I should mention this. This is a domain that's also regulated, doesn't have corners, but it is opening up here, sort of almost having an interior angle greater than pi, but it's actually equal to pi. Anyway, so here is the main result of my first paper with Han. And so it's the following. Let's take this beta that I just described, and let's somehow split it into 2 bits. Okay, and the idea is, so this is, we are free to do this splitting, but there are some constraints. So first, beta plus is non-decreasing. So what this says is that, for example, if I am on this domain and I'm turning here to the left, so that means beta, the argument of the forward, so beta is not the forward tangent vector, it's its argument. The argument of the forward tangent vector is increasing here. So I can just make beta to be equal, or beta plus to be equal to beta, and beta minus just to be 0. Okay, so I want to put the sort of left turns of the boundary into beta plus. But here I'm having some right turns. By the way, if the domain is convex, then I can just put everything into beta plus. So I can make beta plus to be equal to beta, beta minus to be 0. And so if I am now in this part of the domain, then I'm turning to the right if I'm going along the boundary counterclockwise. And so I have to encode that turn into beta minus. I could put also, by the way, this into beta minus, because the only constraint for beta minus that it has to have a modulus of continuity. And so in particular, it has to be continuous if the modulus of continuity is the standard type, which means it vanishes at 0. And so for a domain like this, I couldn't have that because I have a jump to the left in the argument of the forward tangent vector. And therefore, I can't put that jump into beta plus because that's a decrease in the argument. And if I want a continuous beta minus, then obviously I can't put it into beta minus. So for this domain, I would have to have this with a non-continuous modulus of continuity. But if I want a continuous one, which I do, then I can include this domain. And again, so the positive terms of the boundary I can put into beta plus, and then here the negative terms I have to put into the beta minus. Okay, and so, so what's the result now? So we take these modules of continuity. We take some beta plus, beta minus has some modules of continuity, and create this complicated function here. Now, it's actually not that complicated because for most moduli that you ever see, this is just more or less constant times s. Okay, so it's just a linear function. And the reason is most moduli, in particular the Hölder moduli of continuity, are Dini. So the function is then Dini continuous. And that means that the integral from 0 to 1 of this fraction is finite. Okay, so for Hölder, obviously, this is the case. And if that integral is finite, then this whole exponential is basically just a constant. As s goes to 0, it becomes a constant. So this function here is just constant times s. If this modulus is even less continuous than all the Hölder moduli, then it can happen that this integral, if I go all the way to 0, is infinite, and then of course this exponential will be some some function of s. But in any case, if the modulus vanishes at 0, then this is little o of s minus something, s minus any epsilon. And so here's the theorem, and there are two. It's a sharp characterization of the types of domains on which particle trajectories for Euler with bounded vorticities can reach the boundary in finite time. And so there are two alternatives here. And so the first one is if the integral of 1 over this qm is infinite. So for instance, if this modulus is Dini, then this exponential is just constant times s. You take 1 over that, the integral is infinite. Okay, so for all Hölder moduli, for all Dini moduli, this alternative happens. So that means the domain is sort of reasonably continuous, the boundary. And so again, vorticity is bounded. And so the statements are any weak solution is Lagrangian. And in fact, more, the particle trajectories, none of them can reach the boundary in finite time, not just full measure. Or not just zero measure can reach the boundary in finite time. And if the initial condition is constant near the boundary, then the solution is going to be unique. So solutions are Lagrangian and actually unique. And so the other alternative is if I am only able to split this beta into beta plus and beta minus in such a way that beta minus has a modulus of continuity for which this integral is finite. So in that case, and also M is concave, which usually the moduli of continuity are, but they technically don't have to be. So then there exists a domain where the split is like that with that modulus of continuity. And there exists a weak solution that has a particle trajectory starting inside the domain, reaching the boundary in finite time. Okay, so that's basically a sharp characterization of when particle trajectories can reach the boundary in finite time. And know that there is no continuity restriction on beta plus. So we don't care about corners with acute angles. That means a jump in the argument, a positive jump in the argument of the forward tangent vector. And we can just put it into beta plus. The beta plus can have jumps as long as it's non-decreasing. And so in particular, if we take a convex domain, any convex domain doesn't have to be regular in any way, then I can just take beta plus to be beta, beta minus to be 0. And obviously the theorem applies with the first alternative here. And so on such domains, we have that all the weak solutions are Lagrangian. And we have uniqueness if the vorticity starts constant near the boundary. Okay, so let me also tell you about the approach rates to the boundary in the case when the particle trajectories do not reach the boundary in finite time. And maybe I will skip it. We have an exact function. I will skip the description, but this function actually is the double exponential rate. So E2 minus E2 tau, rho tau, for all Dini moduli of continuity, so including Euler. And so it says basically that the approach rate to the boundary is precisely given by that function. So if we start inside some compactly contained domain D prime in D, so the infimum of the distance from the boundary is no less than this function at 300 times omega infinity times time, and we can construct or there are domains on which this distance is less than or equal than this function times another constant of times time. So up to the constant, this is a sharp result as far as the approach to the boundary is concerned. And so here's just an example of what happens on the borderline. So for Dini continuous modules, I already told you that we have this approach rate. So, and again, this is only depending on the modulus of M. So it depends on how quickly the domain, excuse me, how quickly the domain opens up to the left if you go along the boundary counterclockwise. So in here, obviously, you have a jump to the left, and here depends on how quickly this opens. You might approach this point from inside the domain in finite time or might not. And so the borderline case is constant over log R for this modulus, as you can easily see from, so basically the question is when this function has an infinite integral. And so we have constant over log R. So then that's the borderline case. And it turns out when the constant is less than pi over 2, then you get still a double exponential approach rate to the boundary. And of course, this is again for fairly rough domains. So the velocity is not log Lipschitz. You get the same approach rate as for log Lipschitz velocities on smooth domains, but here the velocity is not log Lipschitz, but we're not talking about the velocity, we're just talking about approach to the boundary, and it turns out you get the same rate. But if you take the constant to be pi over 2 exactly, then you get a triple exponential approach to the boundary. So this is what the abstract said, that the condition we obtain is almost equivalent to interior angles at all points being less than or equal pi, because this is really close to not having the interior angle greater than pi, right? So, but if now the constant, by the way, we can also create examples when the approach rate is quadruple exponential or quintuple exponential, etc. And they are sort of refinement of this modulus. But if we take this modulus with a constant a greater than pi over 2, then actually then this integral here is already going to be finite, and therefore we can approach the boundary in finite time. So this gives an example of a domain that does have indeed interior angles, or of them less than or equal pi, but it still can have particle trajectories approaching the boundary in finite time. Okay, so see, I have about 10 minutes, right? So let me just quickly tell you about what goes into the proof. And so this is the stream function here. And we can actually write it exactly using the Riemann mapping, because this involves the Green's function on the domain, but because of the Riemann mapping on our domain, Green's function is just a image of the Green's function from the unit disk, and we know that one very well. So this is the formula for the stream function, and then we have to take grad perp of that, that's velocity. And then we measure the distance here, the distance, oops, doesn't work, never mind. The distance here from the boundary, but of the particle trajectory, but not on the domain itself, but on the unit disk after we map it with the Riemann mapping. And that's necessary to get the sharp result. So it turns out that we can get slightly less sharp result if we look at the domain directly, but if we want to get a sharp result, we need to go through the Riemann mapping on the unit disk. And so then we look at D prime, and it's this complete mess here. But it turns out actually the mess is not so bad. because if we are near the boundary, this is, for example, 1 or close to 1, so we can just ignore that. Similarly, 1 minus this is a 1 minus this squared is about 1 minus that, and that is actually the distance itself. And then it gets multiplied by 2, but that's just a constant. And so if we look at it and simplify everything reasonably, so then we get that the derivative of the distance is bounded by constant times the distance itself times this chunk here, this last line. And there is a determinant of the Riemann mapping here and the inverse here. If these were not there, we could just compute this integral or estimate this integral, because this is just a point inside the unit disk. Okay, so we could just estimate this integral what it is for any points inside the unit disk. And of course, with the determinants, that becomes a little bit more complicated. But if, for instance, we could show that this whole thing is bounded by a constant, regardless of where we are in the domain, then of course this would just tell us at most exponential decrease of the distance. And clearly that's not going to be the case. But if we could show that this is bounded by log of d, then this would give us at most double exponential decrease of the distance. And that's precisely the double exponential approach rate from smooth domains. And so all that is just using the Gromov inequality. And it turns out that actually we were able with Han to show this with this point tx xt to be just c here. So that last line becomes this mass here, and we're able to show that actually this is indeed bounded by a constant times this exponential. This is the same familiar integral we had before. So for Dini moduli, this is just all one big constant. And this goes to 1 minus c. This is distance of this point c from the boundary. So this is exactly the d of t on the previous slide. And then it gets multiplied by this chunk here. And you remember this is that integral that was infinity when the particle trajectories did not reach the boundary. And all this again depends just on m, the modulus of continuity for the beta minus part of the forward tangent vector. The beta plus part only enters through the Riemann mapping into this one constant here, which is almost irrelevant. So this then becomes the integral of this function from distance dt all the way to 1, and that of course will be infinity in the situations where the particle trajectories do not reach the boundary. But it has some growth rate, and actually it turns out if you take your Qm to be a constant times s approximately, if you have a Dini modulus of continuity, then of course this here is going to be growing like log of this point, and this point is d. So this indeed gives you then log d, because this is one big constant, this is log d. So you go back here and you see d prime less than equal constants times d times log d, and hallelujah, double exponential, or at most double exponential approach rate to the boundary. And so the full result is obtained by just getting exact estimates on when this gives you a finite time when d can become 0, and when it tells you d cannot become 0 in finite time, based on exactly this integral. And so that's where the sharp result comes from. And by the way, this all uses some complicated formulas for the determinants of this Riemann mapping at different points, which we found in a complex analysis textbook, and then we used those, and we were able to use them to get the result. And finally, let me mention a second result we obtained with Han, and this one is along the same lines as Lacav's original result. So I told you that there were Lyapunov functions involved, and so in the result that I described until now, the Lyapunov function was just the distance from the boundary if we map everything onto the unit disk. And Lacav, for solutions with signed vorticity, let's say positive vorticity, use a different Lyapunov function, and it is the minus stream function. So stream function is negative, so that's why the minus. So if vorticity as a sign and string function is negative, because you are solving a Laplacian of C equal a non-negative function. And so, so that's now a time-dependent Lyapunov functional, because the string function for the particular solution changes with time. But it has the advantage that the term u dot grad psi is going to vanish. Because, you know, if you want to differentiate it with respect to time, then if your point is moving, you have to also differentiate the velocity u with which the point is moving dot gradient psi. But that vanishes because u is just the gradient perp of the string function. So you take the gradient and you turn it 90 degrees. And so then this dot product is going to be exactly 0. So that vanishes. So the only thing you need to do if you are looking at the time derivative of this Lyapunov functional at a particular trajectory is to look at the time derivative of the string function. And so he did that, and he obtained specifically in C11 domains with finitely many corners that were exact sectors, and none of them acute. He obtained the result that this Lyapunov functional can never become 0 in finite time. And we got under the same hypothesis of non-negative non-negative vorticity, but for much more general domains, the same result. And so the result is this: if you take this beta, this forward tangent vector, again, we have a regulated domain, and now you don't have a freedom to split it. You just split it into the continuous part and the discrete part. So the discrete part are all the jumps. And so, so basically all the corners. And so if the continuous part is dini, and you can measure this with respect to the Riemann mapping, or just directly, you take arc length, you take beta as a function of a point on the boundary parameterized by arc length, and you split into the continuous and the jump part. And so if the continuous part is dini, which is still including all the Hölder moduli of continuity, and then the jumps are such that if you take basically all the points where you have these jumps, which are corners, there could be infinitely many of those. They could be dense even. So if you take each angle and look how different it is from pi, sum those differences. If you get something finite, then this result applies. So in particular, it applies for even infinitely many corners, and corners of any size. You can have you know, a few corners arbitrarily close to 2 pi or arbitrarily close to 0. With angles like that. Okay, so if this applies, then you have the same result. So any weak solution is Lagrangian, and if a vorticity is constant initially near the boundary, then it remains that way. Particle trajectories never reach the boundary in finite time, and therefore solutions like that will be unique. But of course, solutions that are greater or equal 0. Okay, and so I see I have a couple minutes, so just let me just close in here with a few remarks. So first, with Lacan, we showed that all weak solutions were Lagrangian on these domains that were C11, piecewise C11 with finitely many corners with angles less than pi. And we did by sort of taking our solution and extending the velocity and the vorticity to R2 and then applying the de Perna-Lyons theory. And with Han, we were able to do something a little bit better without basically not needing this extension. And instead, we used uniqueness of weak solutions to the transport equation, because the transport equation has the same weak formulation as the Euler equation. Okay, of course, in the transport equation, the velocity is given, whereas in the Euler equation, the velocity is obtained from the vorticity through the Biot-Savart law, but it's the same weak formulation. And so it turns out you can use these results. And so the uniqueness of weak solutions to the transport equation doesn't give you uniqueness of the weak solution to the Euler equation, but it does give you that all such solution or weak solutions to the Euler have to be Lagrangian. Okay, as long as the particle trajectories don't hit the boundary. In fact, we got more. Even if the particle trajectories can hit the boundary, the vorticity is always transported by the velocity until the point the particle trajectory hits the boundary. So that means if you take Tx is the time where the particular trajectory leaves the domain, So up to that point, you take all the x, so all x, so that tx is greater than some t. So at any time you take all the points that are still remaining in the domain, then the vorticity at those points almost everywhere is equal to the vorticity at the points, the original points of those trajectories at time 0. And so using this, it tells you that as long as for almost all initial points, the trajectory stays inside the domain, then actually the weak solution has to be Lagrangian. And so what I'm talking about does apply. And so that tells you there are basically two questions you can ask here. The first one is, can actually happen that you do have a positive measure of trajectories on some crazy domain that leave the domain in finite time? Clearly, you know, if you have just a single angle that's has single corner with angle greater than pi, then it's not going to happen. But you could have some kind of fractal domain. So that's, of course, sounds like a very difficult question. And then the second one is like, okay, but if it doesn't happen on some domain, are then really all weak solutions unique? And that's, of course, the big open question that I asked at the beginning. And we don't know how to answer that, except in these situations when we can guarantee that solutions that stay constant near the boundary for all time are like that because the particle trajectories do not reach the boundary in finite time. Okay, and that's all I wanted to say. Thank you.